Hello, I want to welcome everybody to this CodeLabs talk. I'm super excited that all of you could be here. Today we're going to hear about Vivian, who is a PhD student at Carnegie Mellon. She is going to talk to you about robotics.
Hi everyone. Let me start my presentation. Okay, so my name is Vivian, and I'm here to talk about the road to robotics research, where we are now and where we are headed. Just a little heads up, this is not really a depth talk, but rather a breadth talk, as I'll be giving a very broad overview about the world of robotics, but nothing super specific. So, about me, just like many blossoming nerds, I started with FIRST Robotics in high school. This is a national robotics competition, and high schools from all over the country build robots and compete during the spring season every year. I had so much fun creating the robot that when I went to Columbia for my undergraduate, I decided to do computer science and mechanical engineering in hopes of combining these two and working in robotics. During my time at Columbia, I worked at places like NASA, Disney Research and Imagineering, Conservation X Labs, and San Diego Zoo Global. And with all this experience, I had so much fun, so I decided to apply to grad school to learn even more. So right now I'm a PhD candidate at Carnegie Mellon's Robotics Institute, and that's where I'll be spending my next 5 to 6 years. So let's get started. So robots. What is a robot? When I show you this picture, a robot that looks like a human, that's a lot of people's first thought about what a robot should be. So this is Sophia.
It looks like we can't see you changing slides. It looks like we're just stuck on the first slide.
Oh, interesting.
Yes, now we're good.
Okay, sorry about that. This was my about me slide. Pretty simple. This is my current slide. Okay, sorry. So this is Sophia. She was created by a Hong Kong-based company called Hanson Robotics, and she is a humanoid robot. The creators created her to help out the elderly, help out with crowds, basically just like interact with people, which is why they made her to look like a human. And so to a lot of people, especially due to sci-fi and books and movies and stuff, when they think robot, they think of someone like Sophia. Also, fun fact, Sophia was recently granted citizenship in Saudi Arabia, recently as in maybe like 2 years ago. So first robot ever to be a citizen. But yeah, so we have our humanoid robots. We also have robots that look like this. This is the Mars rover from NASA. They've had many iterations of Mars rovers, and a lot of people, when they see this, they're like, all right, yes, that's also a robot. It doesn't look like a human, but it looks vaguely like an animal. It kind of looks like a dog, honestly. It has wheels, it has code, it roams around on Mars by itself. That's a robot, that makes sense. But then we see things like this. A robot, we have like a factory arm that makes cars, manufactures cars. We have the Tesla, we have a Roomba. People look at these things, yeah, that's technology, but people don't necessarily jump to robotics when they're looking at these types of things. So what exactly is a robot? Robots are where software meets hardware, basically. There's not a really good concrete definition for what a robot is. If you Google it, there's no like defined term that everyone goes by. But here are some criteria that are generally agreed upon that makes a robot. Robots interact with the physical world via sensors and actuators, but any sort of interaction with the physical world. Robots are programmable, so that's where the software comes in. And robots are usually autonomous or semi-autonomous. So what this means is basically when you have like a toy car, when you're controlling that with a joystick, actually, most robots are designed so that they don't need to be controlled from step to step to step, and that means they're semi-autonomous or completely autonomous. And that's the goal with robotics in mind. So let's go back to our previous example. These are all examples of robots. Think of the factory arm. It does the same task every single day. Maybe it picks up a window and slots it into a car door. But with doing this task, it's programmed to do the same task every day. And it has this physical component. This arm has several degrees of freedom. It has a grasper to pick things up. It interacts with the physical object, the car window, and slots it in the door. So that's code running a physical object to interact with the physical world. It's completely autonomous because it repeats the same task over and over, so it fulfills all our criteria. Now think about the Tesla. One thing Teslas are super known for is their automatic driving. The whole point is that hopefully in the future we have cars that self-driving cars where we can just sit back, watch a movie, and let our cars drive ourselves to the destination. So the Tesla is very advanced in this front. It's not completely automatic self-driving, but it does have road assistance. So it can, like on the highways, navigate the cars around it, not crash, kind of like cruise control, but even more automatic coming from the car. So that's all program guiding the car. Program and cameras and sensors so the car knows what to do. But then the physical component obviously is the car, and it's in the real world, it's taking you places. That's a robot. Now we have the Roomba. I don't know if anyone has worked with the Roombas recently. I think they were really hot like 15 years ago. There's still new models coming out like every year, every other year. But nowadays, Roombas are incredibly complex. They can actually be programmed. If you buy a Roomba, you can program it. They have kind of an interface to allow you to program it. They even sponsored a hackathon I was at where whoever programmed the Roomba to do the coolest thing won, and the team that won programmed the Roomba to like make graphs on the floor. So there we go, a robot, a physical component that's being operated by code. So now we know kind of what a robot is, and it's a really broad, expansive field. But there's a lot of subfields, a lot of topics that are in robotics. Unfortunately, you can't break it down super like concretely, just like how you can't define a robot very concretely. There are so many fields. And if you Google like, what are the major robotics fields? Every single website will have differing answers. So I'm going to go into some of the really current topics, the really hot topics in like university research or like corporate research, to hopefully give you a good picture of what is being innovated right now in these labs. So here are some current robotics topics. First up, artificial intelligence. I'm sure all of you guys have heard about artificial intelligence. In fact, I think I saw on the schedule like multiple people talking about this topic. And I know that people have a hard time distinguishing artificial intelligence and robotics. A lot of people think it's actually the same thing. And it's true that there's a lot of overlap. So as you can see from this Venn diagram, you have the robotics, you have the artificial intelligence, and then in the middle, you have artificially intelligent robots. To help you picture it a bit more, a pure AI program, think about AlphaGo. That's the program that can beat humans, most humans, all humans in Go, the board game. So how AlphaGo works is that it computes everything on the computer, and then on the computer will display like what the next move should be. And then how they beat a human component is that there was a human who looked at the computer and then moved the piece for the computer. So everything was happening on the computer, all the AI was on the computer, and it didn't interact with the physical world at all. It was just on a computer. You can't just take that same code and throw it into a factory arm. The factory arm isn't going to automatically then go pick up the piece and move it. You need to have that interface. You need to integrate that code into the robot so that the robot can become artificially intelligent. So that's why there's AI programs, but there's also AI robots. So let's go back to our Sophia example. Why do they want her to be artificially intelligent? Like I said, her main purpose is to hopefully accompany elders in senior care, senior nursing homes, or navigate crowds and like help direct flows of traffic, that kind of stuff. Any situation where there is humans. And humans are unpredictable. I'm sure you've met various old people in your life, what they want to talk about, what they enjoy doing. Each of them is super diverse. So if we have Sophia programmed to do one specific set of tasks, like play tennis, obviously she can't be just a general nursing home robot because not every elderly citizen wants to play tennis. So the goal for Sophia is to become imbued with AI so that she's able to learn and adapt to the people that she's working with, and to the situations, and just like humans, make decisions and all that kind of stuff. So again, it's easiest to put these examples in terms of humanoid robotics because we understand humans as humans ourselves. So when we see a robot mimicking a human, that makes sense to us. We are intelligent and we're trying to give artificial intelligence to robots. But as we go into other topics, you'll notice that AI comes in many, many different forms, and not all are humanoid robots. Speaking of, so our next topic is sensing and perception. And a lot of you already, like I said, are familiar with AI and are probably familiar with a subfield of AI, which is computer vision. And computer vision is very huge in robotics as well. So let's go back to the Roomba example. This was an art project done by someone on Twitter, I think. I'm sorry, I forgot the username. But he basically put LEDs on 7 Roombas and just let them traverse this room and then took a long exposure photo. So it looks really cool, but as you can tell, it also looks very sporadic and inefficient. And how a Roomba works right now, it does have sensing capabilities, but its sensor is a touch sensor. So what it does is it roams around, and when it touches something, as in it's blocked up by like a wall or something, it'll turn, I think it's like a random amount of degrees, and then just go a different direction. And the idea is if you put it in a room and just let it roam there for a while, it'll clean the whole room, because eventually just by randomly traversing the room, it'll probably reach pretty much the entire surface area. So that's a current day Roomba with very basic touch sensing capabilities. But what if we were to give it computer vision sensing capabilities? With computer vision, you're using cameras to be able to understand what is in front of you and process that and react to it. In case of the Roomba, it would have a camera that looks at these objects. If you see like these blue squares looking at these objects, so it's seeing this, that's the input is the camera image of the objects. It processes it by denoting them as objects, recognizing those are objects, and then it reacts to it by avoiding these objects. This would be an upgraded level of sensing capabilities, because this way it doesn't have to sporadically traverse the room. It can somewhat understand the room and then traverse the obstacles in the room so that it can maybe clean the room in a less sporadic, more efficient pattern, by using cameras to process the input and then navigate. So computer vision, I think that probably is familiar to a lot of you, and again, makes a lot of sense. But the cool part about robotics is that sensors are not just camera based. If you think about humans, we have our 5 senses, right? Hearing, smell, taste, sound, touch, or sight. I think I said one of them twice. You have your 5 senses, and that gives you a really complete worldview. Right, when you're eating food, you don't just look at it to figure out what it is. You smell it, you taste it, you could hear it, I guess. Like, you are processing all these different senses and putting them together to figure out what it is you're interacting with or looking at or something. So when we're talking about sensing with robotics, we're not just talking about cameras and computer vision and sight, but we're talking about the other senses too. So here's an example. As you can see on the left, we have this kind of robot skin. It's a robotic hand. Someone's shaking it. A real hand is shaking it. And this looks obviously just like a human hand. So this is a technology that is pressure sensor based, basically. So if you think about having a mapping of pressure sensors on this robot hand, they tell you how much pressure is where. So if you're poking the middle of your palm, for example, there's probably a lot of pressure in the middle of your palm and very little on the outsides of it. So based on this, if you have a map of pressure sensors that's communicating with each other, you can probably figure out, oh, there's pressure in one point in the middle of the palm. Okay, that's a poke. How the robot's supposed to interact to someone poking your hand, not entirely sure. But then if you think about like a handshake, when you're gripping the entire hand, there's pretty even pressure, I would say, along the palms, and maybe like a lot of pressure on the outsides of the hands because you're gripping the hand, right? So if we have a robot that has a bunch of pressure sensors mapped along the hand, when you slide your hand in and grip the hand, the robot can then process that pressure map input and think, okay, so someone's gripping my hand, what do I do now? And if someone's gripping hand, you're probably shaking it. So that's how the robot then reacts to that input, shaking the hand. And so this is a type of sensor that doesn't rely on cameras basically at all. It's working with the touch sense. And if you can imagine, we have the touch sense, the sight sense. There are various different sensors that you can integrate with robotics in order to emulate the other senses that we have as humans. So sensors and sensing and perception, that's a big part of robotics, but definitely don't be confused with only thinking that's about cameras. Okay, I see that there's a question. It's not letting me open it, but I will do a Q&A section at the end of this talk, so just FYI. I don't know why I can't see the question.
I can just read it out to you. It says, does touch sensing by Roomba cause damage since it has to collide with an object in order to recognize it?
Does touch sensing cause damage?
Mm-hmm.
Well, it depends on what kind of touch the program is, the robot is prepared for, right? So if you have this kind of hand robot, if you were to like punch it really hard, it would probably break the robot. I mean, like these kind of sensitive small sensors are often not made for this kind of for a kind of rough application. Honestly, a lot of electronics are really fragile. I'm sure you recognize even from like your phone, when you drop it, it breaks. So a lot of like these sensors are pretty fragile, but there are ways to kind of negate that if you're trying to make something that's supposed to be hit hard. Like for example, if you have a punching bag with a vibration sensor, and when you punch it, it like calculates how hard the punching bag vibrates and maybe tells you like good punch or not strong enough. I don't know. That would be the reaction to the input, which is the punch. You can have a vibration sensor buried deep in the layers of fabric, but have it be a sensitive vibration sensor so that when you punch the fabric of the punching bag, it can still feel the vibrations. And then you got to use like some kind of math to calculate like how strong was that punch. But yeah, definitely lots of sensors are not very durable. So for an example like this hand, it probably isn't suited for any kind of a rough application. Yeah, okay, so next topic, human-robot interaction, going off of that hand example. So like if you think about the hand example that I was just talking about, that obviously makes sense when we're talking about humans interacting with a robot. But you know, there are a lot of robots that are not designed for humans to be anywhere near the robot. So if we're thinking about the factory arm, it's repeating that task over and over and over again. And the point of that is actually so that humans don't have to be on the factory floor. It can all be operated by robotic arms. So there's an entire branch of robotics that's dedicated specifically for human-robot interactions, robots that are interacting with humans. And the thing that makes this part unique is that these robots take human input and react based off of that. So I'll give some examples to make that more clear. I don't know if you guys know Baymax. So Baymax is from my favorite Disney movie, Big Hero 6. I actually watched that movie the year before I went to college, and that made me convinced that I was choosing the right thing, because I was like, oh man, I decided to do college last minute decided to do robotics last minute before going to college, and now I'm watching this movie right before like going to college. Like I must be like, I need to do robotics. But anyways, so Baymax is a healthcare robot in Big Hero 6. His whole job is to notice when people around him are in distress or hurt and evaluate them based on asking them like on a scale of 1 through 10, like how painful, how much in pain are you, or like scanning them, doing some kind of body scan and figuring out like if they have a broken ankle or if their feelings are in distress or something. So basically a healthcare robot that interacts with you personally. And actually, Baymax is a real robot. Oh, that is not a good picture. Sorry about that. But Baymax is actually based on a real robot from Carnegie Mellon. Professor Chris Atkinson was creating this robot to be kind of a robot companion, and CMU used to have a partnership with Disney, so some Disney executives were over and they saw this robot, and somehow we're just like, oh man, we got to make a movie about a robot. Let's do this one, and Baymax came to life. So obviously, in person, Baymax is not quite as cuddly or friendly or cute in any way. He's actually kind of terrifying. But you can see that there's like an inflatable shell to protect the robot's insides and protect you from the hard metal robotic insides. And the point of real-life Baymax is also to be kind of a healthcare robot. So that means it's interacting with humans. It's asking humans for direct input, such as, like, how are you doing today? Where does it hurt? That's direct. It's taking direct human input and then deciding what to do with that, like maybe offering a band-aid or giving the human a hug or something. But it also takes indirect human input. So if you think about Baymax, like when he is in a room and someone says ow, he's supposed to respond to that and go over there and be like, why did you say ow? Why are you hurt? Where does it hurt? The point of Baymax is that it can notice humans that are not directly interacting with it, but can detect that they are in pain in some way. And that could also mean like Baymax looks around the room and notices that like human C is frowning and the rest of the humans are laughing. So go to this human and ask like, what is wrong? So it's taking direct and indirect human input and deciding how to respond based on that. But again, Baymax is a humanoid robot, so it's a lot easier for us to kind of comprehend how Baymax would react, the input that it's taking in, and how that Baymax should respond, because like that's what doctors do, right? They interface with humans, they ask questions, they prescribe treatments. This is an example of a humanoid robot taking place of human-human interaction to become human-robot interaction. So I'm going to give you an example of a non-humanoid robot that also interacts with human and is part of HRI. So let me know if this video isn't playing right.
Here about our work on using eye gaze for assistive manipulation. Robots are used to help people perform many tasks, from remote surgery to space exploration. One exciting use is for assistive robots, or robot arms that mount on wheelchairs and help people to perform activities of daily living. However, teleoperating a robot to perform a complex task is very difficult for people. Controlling a 6-degree of freedom manipulator arm with a low-dimensional input device is not intuitive, and handling contact in the workspace makes the problem even harder. To make the problem easier, we can add autonomous behavior. The system infers what the user is trying to do with the robot, then provides a signal to assist in the task. People's natural eye gaze is a powerful signal for understanding their intentions. People's eye gaze behavior while they manipulate objects with their hands has been a topic of research in psychology for decades. While using their hands to perform tasks, people look almost exclusively at the objects they are trying to interact with or avoid, and rarely look at objects that are not relevant to the task. In this work, we show how to use mental state insights from gaze behavior robot assistance. First, we collect data on people's eye gaze behavior while they teleoperate a robot. Next, we develop a pipeline for automatically processing raw eye gaze into a contextual representation. Finally, we discuss 2 types of assistance that the eye gaze signal enables. To understand what people look like while teleoperating a robot, we performed a study in which participants were asked to spear a marshmallow using a fork held by the robot. In this study, we found that, likened by hand manipulation, people look at task-relevant objects, particularly the morsel they are trying to spear. However, people also spend a lot of time looking at the end effector of the robot. We found that when something goes wrong in the task, for example, the robot goes into a bad kinematic configuration, people look at the source of the problem. These insights enable us to design gaze-based assistance strategies. Next, we process the raw gaze data into a lower dimensional and context-rich representation. The raw eye gaze data is first clustered into individual fixations. Each fixation is labeled with an object in the scene. This sequence of labeled fixations enables machine learning approaches for intent recognition. Finally, we introduce 2 strategies for incorporating gaze into assistance. First, we discuss inferring people's goal from gaze. Earlier work infers people's goals from their controller input. We note that gaze provides a complementary signal for inferring people's goals. The joystick input provides immediate direction towards the next step, while gaze gives absolute information about the final goal. Second, we introduce a new type of assistance, responsive obstacle avoidance. Here, we've hypothesized that people will look differently at obstacles depending on how concerned they are about them. It will be reflected in their eye gaze behavior. Therefore, we can design an assistance strategy that measures their sensitivity to a particular object and adapts the robot's trajectory accordingly to give sensitive obstacles a wide berth and more efficiently move around safer obstacles. In this project, we use eye gaze for intention inference to broaden the possibilities for assistive teleoperation and more generally human-robot collaboration. Thank you.
So, this is a project from Carnegie Mellon's Human and Robot Partners Lab, which is just like a fun little way of saying human-robot interaction. And there's a lot of technical terms in the video, but I wanted to play the whole thing in case anyone wanted to watch the whole thing. But the gist of it is that basically It's really difficult to operate a lot of complicated robotic machines. Like if you think about an arm with a bunch of 6 degrees of freedom, you have a wrist joint, an elbow joint, a shoulder joint. The shoulder joint can go 360, the elbow joint can go back and forth, the wrist joint can go 360. Like it's a lot to think about if you're trying to do something like getting this robot arm to pick up a marshmallow. When you're using a simple joystick, it's often really hard for users to be able to control it so precisely in order to just go pick up that marshmallow. So this team created an interface that basically reads your eye gaze and looks at what you are looking at in order to then have the robot kind of autonomously move, have an autonomous plan and autonomously move to help you with your task. So if you're imagining you're trying to control this robot to look at the marshmallow, you're probably looking at the robot hand, and then you're looking at the marshmallow that you want to pick up. And honestly, you're probably staring pretty hard at the marshmallow you want to pick up. So the robot sees your gaze they have like these kind of lens things that you wear, so it can like track what you're looking at. So it sees where your gaze is going. It sees that you're looking at the marshmallow. So the robot arm will then try to position itself like directly above the marshmallow, so you don't have to do it so precisely with the joystick. It'll help you. And then of course you can lower it, and then you're still staring at this marshmallow. The robot arm is like, all right, okay. Input is that she wants that marshmallow, or input is you gazing at the marshmallow. The processing is like recognizing that you probably want that marshmallow, and the reaction is that it helps you try to pick up the marshmallow as precisely as possible. So it's kind of like assistive. So this is also a human robot interaction. For this specific robot, all they really tested on is like picking things up. But in the future, this could help a lot with like people who are disabled and maybe don't have full use of one of their limbs, and it can help the guide. So the eye gaze can help the robot determine what this person using the robot wants to do, and then help them with it with less and less like actual physical input that the human has to do. So yeah, this is, I mean, an arm is still vaguely humanoid, but overall it's not a human robot. So it's a better example of like the type of human robot interactions that happen in this field. So yeah, those are three really big topics in robotics right now, I would say. And from my examples I told you, you could probably gather how AI is really important in like all those fields. So again, they're not exactly subfields. Like HRI and sensing and perception are not subfields of AI. It's more like, again, Venn diagrams of like artificial intelligent robots, sensing and perceiving robots, and then like the middle intersection is like AI using sensors and perception robots. So these are like a bunch of other fields of robotics that I'm going to just go over quickly. I obviously don't have time to give too many examples for every single one because I want to continue on, but so these are very common robotics topics: mobility, manipulation, navigation. These are more general robotics topics. When we're talking about manipulation, we're talking about robot grasping, and that sounds like such a specific problem, like robots picking things up, but it's actually a really big research issue right now. Because our hands are so complicated. There's so many joints, there's so much going on. We have opposable thumbs, which like most animals don't even have. So having a robot have that kind of same grasping technique is very, very difficult. But also, if you think about it, like not everything has to be modeled after humans. So when we're talking about manipulation and grasping of objects, they don't need a hand. One thing that my lab at Columbia did is they had kind of a vacuum suction cup with a film over it. So to grasp things, the film would go over the object, so it molds to the object, and then it uses vacuum suction to pick it up. And that way it could pick up all different types of objects without having to manipulate so many joints. Mobility, that's kind of like how a robot moves. Legs are actually not really the best way to move. That's why most animals aren't bipedal. Legs cause you to be a lot more off balance because you only have 2 points of contact, whereas like quadrupedal, I forgot the word for that, quadrupeds, with their 4 points of contact on the ground are a lot more stable often. But also with robot mobility, you can have wheels, you can have, all different ways of moving. And then along with that, navigation, that's like a lot of the self-driving stuff I was talking about. So navigating various environments, that's huge because there's so many different environments in the world. You can talk about navigating busy city streets, and I think that's the most common problem, especially with self-driving cars. But there's also navigating like a forest or navigating the treetops, and how do we get robot to navigate these things. And it's very tied into obviously mobility. How do we have it move? How do we have it navigate? There's a lab at CMU that's doing snake robots. So that's a completely different form of mobility and navigation than any like Mars rover or anything. So these are kind of field robotics. That's a broad term to describe these, but these are very simple: aerial, aerospace, underwater. They all present their own challenges, as you can imagine. And those are big topics right now. If you want to go to NASA, aerospace robotics is for you. Yeah, so those are pretty self-explanatory, I think. Nanorobots, robotics, and bionics, those often fall more into the biotech robot sphere. A lot of people are very interested in biology and want to integrate technology more into biology. So bionics, thinking about prosthetics that can actually, the way that the robot I was talking about that measures your eye gaze and decides what you want to do, prosthetics that do the same thing, like an arm that can kind of read what you're trying to do based on body cues, like your eye gaze or your body positioning, and then go help you do what you're trying to do with that prosthetic bionic arm. And then you have nanorobotics. That's not just biotechnology robotics, obviously, because there's so many different reasons why you would want like a tiny robot. But a good example of that is that at MIT a couple of years ago, they made this robot pill that you swallow. It was a very simple robot. You swallow it, and then somehow it got something out. If you had something stuck in your stomach, it would like hook onto that and then help you flush it out the next time you go to the bathroom. I don't know the specific of that one, but you should look it up if you're interested in nanorobotics. And then finally, these are kind of some miscellaneous stuff. Teleoperated robotics, that's the category that kind of breaks the definition of robot that I said before, because teleoperated robots are robots that you control completely and they don't have any autonomous capabilities. But they're still often considered robotics because these were how robots originally were. You had factory arms that didn't work on their own, but rather someone operated them from afar. So that's probably like more of an older category of robotics, but for all intents and purposes, it's still considered robotics today. And then swarm robotics. As you can tell from a lot of my examples, the way people are envisioning robots right now is when robots are interacting with humans or with their physical environment, like picking things up or walking through a forest. But when in the future, if all these robots become normalized, then robots are also going to have to interact with each other. It's not just going to be human-robot interaction. It's going to become robot-robot interaction. And with swarm robotics, the whole goal is to make like swarms of robots that kind of interact together harmoniously. And the best example of this is like drone swarms. I don't know if you guys have seen any of these videos, but there's videos of drone fireworks. So instead of traditional gunpowder fireworks, they have drones, like 1,000 drones equipped with LEDs in the air, forming various patterns and moving in conjunction and like making images in the air with LEDs. And I think it's very beautiful and way more eco-friendly than real fireworks. So I'm a big proponent of swarm robotics for that purpose specifically as well. So yeah, these are a bunch of the different fields of robots. And like I said, this is not a non-exhaustive list. You can definitely find much more online. But where is robotics headed? That is the question here. I talked about the road to robotics, where we are now. We covered that, but where are we going? And why is this important? Why do you guys need to know about robotics? First off, the software needs to catch up. I know that in this CodeLabs, probably all of you guys are programmers, and like so you guys are well versed in software, and the robotics field right now really needs software engineers, really needs computer scientists to join the robotics world. That's why my PhD, even though it's in Robotics Institute, we're under the School of Computer Science, so it's actually a CS PhD. And then if you go to Stanford or like any of the other major robotics schools, the PhD you get if you're working in robotics is always in the computer science, is almost always in like computer science instead of mechanical engineering or electrical engineering. That's because we have a lot of complicated robots available right now, But when you don't have any code in them, they're just basically fancy hunks of metal with a lot of expensive sensors in them. So here we have the PR2. This is a very common research robot. So if you go to most robotics labs, like in the country, probably one per school will have like a PR2 in it. It's basically a super, like tons of sensors on this humanoid-ish robot, and people buy this base so that they don't have to make like custom build their own robot, and then they could just add code to this robot so that it works. So that's a very common research robot. And then on the right, we have Boston Dynamics Spot robot. It's more of a dog-like robot. And again, this is available for research now. A lot of research labs are buying this so that they can have the hardware that they can then import code onto. And the software is the part that matters, right? Like you can have this PR2, you can program it so that every time it sees something walk by, it waves. That could be its whole functionality. You can write the program that does that, or you can program it so that the PR2 recognizes trash instead of humans, and then it can go around picking up trash, or it can go into the recycling bin and sort the glass from the plastic. Basically, it's like limitless possibilities what the PR2 can do based on what it has, but it's up to the programmers to decide what it is going to do. The hardware's there, it needs the software, and it needs innovative software to be integrated into it so that it can do cool things that no one's thought about yet. So robotics right now really needs programmers because it has a lot of the hardware figured out, but it needs to figure out the software part. Also, even if you're not interested in robotics necessarily as a career, it's good to know about this stuff because robots are the future. McKinsey predicts that by 2030, 1/3 of American jobs will be automated. And this is because a lot of automatable tasks are very repetitive ones. Like if you think about the factory arm again, slotting the car window into the car door. It has to do that to thousands of cars every day. And it's pretty much the exact same thing every time. Same shape window, same shape car door, same position. It can do it for days on end. And a lot of jobs have those kind of repeatable tasks. So if we're thinking like a Starbucks barista, they probably have to make a lot of lattes in one day. And the latte making process is fairly similar, even though there could be substitute ingredients. It's kind of, froth the milk, mix the ingredients. I worked at a boba shop and not a coffee shop, so I don't know how to make coffee. But at my boba shop, it's combine the milk, combine the tea, add the boba, you got your drink. So if you think about how that can be automated, you can have an arm that easily, one arm for tea, one arm for milk, combine them in the correct ratios, since robots have the ability to be very precise, and then scoop in some boba. And that can be automated super quickly. Unfortunately, there's not a great pipeline right now for retraining workers whose jobs might be replaced by automation. And I'm hoping that that's legislation or something that will be passed in the near future. But also, unfortunately, right now, not a lot of people are thinking about robots. They're not very huge right now. They're not everywhere in the world yet. So to a lot of people, robots are a thing, but it's kind of like this distant or even sci-fi-y thing that isn't going to occur anytime soon. But with the rate of technological innovation, there's going to be a huge boom where robots become the norm, like very quickly. I mean, they are kind of right now very quickly. So I think it's really important for everyone to know about robots and kind of understand how they work, what fields they're in, what tasks they can do, and what research people are conducting in order to be better prepared for the future in which, I don't know, maybe a robot revolution will happen. People joke about that, but it's a little worrisome. So that's why it's always important to learn about robotics and what's going on right now, because in 15, 20 years, what's being researched right now will be probably pretty common in the actual world. Definitely keeping up to date with this stuff is very helpful. But if you are actually interested in starting on this path rather than just knowing about it, these are some steps that I created. This is like the one part of my presentation that I kind of went from my own experience rather than making sure to verify with like real sources online and everything. because this is basically the path that I took. So step number 1 is to learn. A lot of you people, as I said, are probably programmers because you're doing CodeLabs, which is a really awesome program, honestly. But if you're trying to go into robotics, knowing just programming isn't enough. Again, robots are where software meets hardware. So you want to be learning part of the hardware side too. So even if you are a programmer in robotics, you'll at least understand the hardware that you are programming. The most important thing here then is embedded systems. That's kind of low-level programs that interface with hardware. If you guys have heard about in Arduinos or Raspberry Pis, when you add a bunch of sensors and wires to that and you program it to do something, that's an embedded system. And so it's very important for embedded systems to know C or C++. Most of my internships have been in C or C++. Some have been in Python. That's mostly all like what I've been doing in all my internships. So very good to review that. Electrical engineering is also a really stellar thing to know. It's not quite as important because you probably, especially if you're doing pure computer science research in the world of robotics, you probably don't need to actually make a robot from scratch. Like I said, there's a lot of commercially available robots that you can just throw code into, so you don't have to actually create the robot. But it is good to understand circuits and like signals and systems. I personally would recommend taking just the Intro to Electrical Engineering course, and if you have time, taking the one course above that. I didn't even have time to do that, so it's honestly okay if you don't, but definitely the Intro to EE class is very good for kind of understanding these circuits. If you are ever going to need to add a sensor to one of your circuits, you don't want to accidentally, I don't know, overload the circuit, short circuit it, fry your components. I've definitely done that before in my EE lab. It was not fun and very scary. So it's good to know about these kind of things. And then physics. I know that's the subject that everyone's like, ugh, this is the worst. When am I going to apply this? At least at my school and like at my friends' schools, it seems like a lot of the engineers I talked to just hated physics, and I definitely was one of those. But your intro to physics classes, what you take, I don't know, maybe freshman and sophomore year, if you have to, those are actually quite useful in terms of understanding the physical robot. Because if you imagine, again, our arm example, we need to know the strain on the arm if it's angled at this degree and it's holding onto a 50-pound weight, because there's way more shear on the shoulder than if it were angled at this degree and holding at a 50-pound weight. Understanding the physical constraints of the robot, how physics and gravity and weight might affect the robot, understanding the space, the angles that the robot can travel, the robot arms and limbs can travel through. Those are all really important, and a lot of those formulas come from intro-level physics. And honestly, it's not really physics, but mechanical engineering physics. They're kind of the same, but mechie physics is a lot more applied. And that's why I took a mechie minor when I was an undergrad. So a lot of mechie physics helps out with a lot of these things. And I even at Columbia, the robotics classes were actually all under the mechanical engineering department. We didn't have any under the CS department, which was super weird to me. But even in the mechie classes, you were coding. But yeah, so the physics from mechanical engineering, intro mechanical engineering physics is super useful in terms of the hardware. So once you've learned all that, you don't need to be an expert. Just learn the basics of each of these things. You're ready for the next step. The next step is to ideate. What do you want to build? If you're going into robotics, you probably have, well, you could also just like robotics, but there's probably something you want to build, something really cool that could help you out. Like for me, from when I was small, my grandma hates how dusty her windows are, but as she got older, it got harder and harder for her to clean the robots. So I remember being 12 years old, and I'm like, man, I could just maybe like make a robot that does that. I don't know. At the time, I didn't really know what a robot was, but I was like, I bet a machine can do this. Like a machine washes our clothes. Why can't they wash our windows? So what do you want to build? Start thinking about like the fields you want to go into maybe, and what robots excite you. And then how are you going to build it? This part is really interesting right now in robotics because, for example, a window cleaning robot. When I was young, my thought was just a robot that is basically a human. It uses a window scraper to clean the robot. But we as humans get so stuck in thinking about how we would do something that we forget that robots don't have the constraints that we do. Robots don't have to be bipedal. They don't have to have 2 arms. They don't have to stand up tall and like have the same motions that we do. So instead of a robot that stands on the ground and sweeps the windows, how about like a Roomba that works on the vertical surfaces to clean the windows? Roombas already work for floors. And so thinking about like, is it going to have human-like movements, or is it going to be its own type of robot? How to build it, that's very important. And then why build it? I put a little heart here because I think this is the most important thing out of all of robotics, is why are you doing this? Sure, some robot projects might just be cool and you want to do them because they're cool, but there's so much that robotics can do in the future. Robots can vastly improve our quality of life. At least I believe they will, in terms of like cleaning up litter or accompanying the elderly. These are all examples I gave today. These are things that can improve our lives, and these are oftentimes jobs that humans don't want. Like, no one's really getting paid to go swim in the ocean and pick up plastic, but we can make a robot that does that 24/7 for free. That would be awesome and would really help our environment. So why do you want to build this thing? What impact will it have on our future? Thinking about the consequences of the robots you want to build. So you've learned, you have a foundation, and you have ideas. What do you do now with all of this in your head? You fiddle. And notice I said fiddle and not work. I think right now, especially with everything that's going on, internships are hard this year. They're going to be hard next year. I personally had 2 internships canceled literally this past year because of coronavirus. So it's a tough time, and I know that. But there's ways that you can fiddle without having to go find an internship in robotics. Hackathons. I loved hackathons in college, mostly because I've terrible time management. So I could never discipline myself enough to constantly doing a side project. Instead, once every 2 or 3 months, I would choose a weekend and go to a hackathon. Don't think about homework. Don't think about social things. Just work on a project for 48 hours and grind out some of the ideas in my head. And every single time it sucked, but it was so rewarding at the end when I had a product that I could show people that worked, usually, sometimes didn't. And it's really great to just rapidly prototype anything that you're thinking about. Especially at hackathons, they often provide you with hardware, so that's awesome. A good way to get experience is school research. I know that at many schools you can do research for work study, which is awesome because it's like doing a job basically. But even if you can't do it for work study, you could just do it for free. Professors love free labor, but it really gives you good insight into current day research in robotics. And it really lets you build up the skills that you've been learning on paper and applying it to actual projects. And finally, side projects. Like I said, I struggled with doing consistent side projects because it always felt like there's so much to do. But I do think this is something really important if you are someone who can manage your time that well. If you get a rudimentary Arduino and sensor kit set, should be like less than $30, and you can start fiddling and making side projects, and it could be the simplest thing. I have my roommate rigged up an Arduino and LEDs all along the roof of our room, and basically when you walk in, the LEDs turn on. When you clap, the LEDs change color. When you do something else, the LEDs dim. Like super basic things, but it required her to wire things. It required her to code things, and so that's basically robotics. It's embedded systems. And so also Raspberry Pi, I would highly recommend. They're basically mini computers, whereas Arduinos can only run code in loops. So if you can get an Arduino, a Raspberry Pi, and some sensors, you're set. You can make so many things as long as you have the ideas and the motivation to do so. So thank you. This is my talk. Oh, this is you guys don't have to watch this, but this is the spot doing a little dance. Again, why build this? This one was purely just this dance, just because it's cool, but this robot's actually very, very complex and an incredible robot. Probably maybe my favorite robot. Okay, you guys can watch that on your own. But dancing robot. So thank you for listening to my presentation. These are my contact info on every platform. My username is Shen. So that's the like LinkedIn, DevPost, GitHub. I don't know what else I own, but I always take that username. So you can find me at Shen. And then that's my school email, vhshen@cmu.edu. Feel free to email me if you have questions or want some resources. I'd be happy to talk, especially right now because not doing much since my internships got canceled. But yeah, thank you for having me, Cora and Tyler, as well. This has been fun. And
Awesome.
yeah.
We really enjoyed having you. Do you want to start the Q&A now?
Yes. There's like 10 minutes left for Q&A.
All right. Let me know if you can pull up the Q&A on your screen.
I can, but I'll have to stop screen sharing. So let me just, oh, there we go. Okay, so do you think doctors will be paid less or become redundant in the future due to the rise of AI and robot technology? So depends on what types of doctors. This is already happening. If you have heard of an anesthesiologist, wow, that's a hard word, anesthesiologist, that's someone who kind of uses scientific measurements like weight, height, medical conditions, data, whatever, to prescribe the correct level of anesthesia to patients who need it for surgery and all those kind of things. That was a very high paying job maybe 20, 30 years ago. And because like if you predicted the wrong amount, the patient could die or feel all the pain. It was very, very important. But right now already, anesthesiologists have been replaced by computers who do basically the same thing. It's not a robot, but it's like a computer where like you type in all the facts and everything and it prescribes the right amount of anesthesia. And it's been very accurate. So anesthesiologist already really isn't quite a job anymore. I mean, it still is, but it's quickly being phased out. So I think this will happen to various doctors over time. Specialists, maybe not. There's also already surgery robots. Intuitive Surgical is a very big surgery robot company, and they have incredible robots. Really great company. You guys should check it out. But basically, that allows a surgeon to remotely operate a surgical robot, so that if your surgeon is in like Maine, but you need surgery in California, the main surgeon can just get on this online platform and operate this robot remotely, so that the robot will do surgery in California. And so that's also, then you don't need as many surgeons everywhere because you can have just the really good ones operating on everyone from wherever they live. So yes, I do think some doctors will be phased out in the future. And I think that's the case for a lot of jobs, honestly. Where can people find inspiration for robotics ideas for side projects around the house? What resources are available online for us to get started? Oh, that's a great question. This is probably a little cheesy, but the best inspiration is what problems you have in your daily life. Basically, anything that you find inconvenient, you could probably innovate something to make that easier. Like if you hate folding your clothes, you could think of a clothes folding robot. You can look it up. I'm pretty sure that's already been made, but you can look at what people have already designed and improve upon that. That's also very innovative. And even just making something that someone's already made is really hard often because you have to follow all the wiring, you have to code it and everything. So that in itself is a side project. But think about any issues you have. You hate washing the coffee mug that you use every day, but you don't want to chuck it in the dishwasher because you only run the dishwasher 3 times a week. Make something that just washes the coffee mug. Yeah, so think about problems you have and ways that it might be able to be solved. As for resources, you can look up Intro to Raspberry Pi and Intro to Arduino. Actually, if you buy a Raspberry Pi, they send you a whole online PDF magazine for basic Raspberry Pi projects to get started on. And if you want to not buy any hardware and you want to just start with programming robots, I do believe there are some services online where you can I'll hold off on that one because I don't know the exact name, so I don't want to tell you wrong. But yeah, you can definitely just Google Intro to Raspberry Pi, Intro to Arduino, and those are probably the best platforms to get started on because they are very much made for the hobbyist, for people who are just working on this stuff at home. how does the camera translate the eye gaze into something the robot can understand? So I would highly recommend going back to that YouTube video. I guess if you email me, I can send you the link. But essentially what happened is that they gathered a lot of data, and so they pinpoint where the eye gaze is looking at, and then they do clustering. So clustering is like taking maybe, so they're getting data points every second, probably like a bunch per second. Maybe let's just say like 20 data points per second as to where someone's looking. So they'll cluster that data and give the robot kind of coordinates. So a camera is 2D, right? Like on my camera, like right here is pixel number, I don't know, 200 by 400. I don't know how pixel numbers work. So they'll cluster the gaze pinpoints, like those 40 gazes over here, into one pinpoint, probably averaged in the middle, and they'll say 200, 400, 200 by 400, that's where the area of interest is. And so then you use linear algebra. That's very important subject to learn. Linear algebra to translate the 2D coordinate into a 3D space. And by doing that, then the robot can know where pixel 200 by 400 is in the 3D space and then move accordingly. If you're doing computer vision, I would say linear algebra is by far the most important math you should know. Does anyone else have any questions? If you think of anything later, like I said, feel free to email me or something. Okay.
All right, that looks like it's just about it for today, question-wise. I really want to thank everybody from coming here, and I want to thank Vivian for giving this amazing presentation.
Yeah, thank you for having me.
Thank you. Bye.
Bye.